Okay, AP Chem class, this is day 60. This lesson is on VSEPR, which is the method we use to determine the geometry, the three-dimensional geometry of molecules. Another aspect of VSEPR is it tells you whether a molecule is polar or non-polar. Most of you have had something about vectors in physics. You may or may not remember much about it. So let me just give you a quick review up here in the upper corner of the assignment sheet. So a vector has an amount and a direction to it. So if I draw this vector right here, and that vector could represent a velocity, an acceleration, a force. There's a lot of things in physics that are vector quantities. In this case, let's say it represents a force, and let's say it's a force of 5 newtons, which is the unit of force in the metric system. Now, if I drew a second vector, and it was exactly twice as long, then that means it would represent a force of 10 newtons. So the length of the vector tells you the amount of the number, which in vector terminology is called the magnitude of the vector. So a vector has two things. It has an amount, a magnitude, and a direction. These two vectors are going in the same direction. So you could add these two vectors together. Even though they're in different locations, that doesn't matter. As long as they have an amount and a direction, that defines the vector. So I could move the 5 Newton vector over here. I'll just sketch it over here real lightly. There's the 5 Newton vector. I just moved it. So this moved to there. Now I have a 15 Newton force vector. So one person was pushing with a force of 10 newtons and another person pushing with a force of 5 newtons. Together they would be pushing with a force of 15 newtons in that direction. Similarly, you could subtract. I could take the 5 newtons, if I flipped it around, pointed it in the other direction, it would be 10 newtons minus 5 newtons. So as long as vectors are in line, you can just add them arithmetically. Just use basic arithmetic to add them. For the vectors we're going to be dealing with, they aren't always in a nice straight line, so you have to break them into components so that they are in a straight line. Now, what do we use these for? If a molecule, let's just say H2O, and we know that oxygen is more electronegative than is hydrogen, therefore the electrons are pulled towards the oxygen. So this arrow represents a force vector that's pulling those electrons toward the oxygen. So those are force vectors. I should make them exactly the same length to be precise. Okay, so now how do you add those two vectors? They're not parallel to each other. They're not opposing each other. They're kind of at an angle to each other. What you can do is break them into x and y components. So let's say this vector is broken into an x component, and what it does is it goes straight up the y-axis, and it goes as high as this line is right here. So it should be right there. And then this vector, you can draw a vector on the x-axis that goes this far, and I can draw an arrow, and it goes as far as this arrow is right there. So I broke it into a y component going vertically and an x component going horizontally. I do the same for this. I can draw a component vector that goes as far over to the right as this arrow is right here. So if I draw a dashed line, it should connect the two. And I can draw another vector up like this, and it should go as high as this arrow, so I can connect those two with a dashed line. So now what I have is I have two, there's a y vector, and this is the x down here. So now I have two y vectors, and you can see they both point in the same direction, upward. So we can then add them together, and I'll do that off to the side here, to get a resultant vector that goes up, and it should be twice as long as each of these. Since these two vectors are equal, it should be twice as long. Now, what about these two vectors? They're going in exact opposite directions, and they're equal in magnitude. So what do you do with those? You subtract them, or in effect, they cancel out. So you have no vector. You have no vector going in the horizontal direction, going this way. Okay, I'll just X that out. It doesn't exist. That means the only net vector from this water molecule is upward. In other words, it's towards the oxygen atom. And what that means is that water is a polar molecule. Okay, it's polar. All right, let's take another example, carbon dioxide. Carbon dioxide is a linear molecule. It has a carbon in the middle. It has two oxygens, one on each end. So it's actually shaped exactly like I'm drawing it. It's linear. It forms a straight line. So oxygen is more electronegative than carbon. Therefore, there's a vector pulling straight in this direction. There's nothing above or below the carbon to pull anything upward or downward, so it's strictly to the right. And then this oxygen also pulls equally in the other direction, like that. So ideally, I drew those two vectors to be the same length, and they're centering right there on carbon. So since you have a vector going to the right and a vector going to the length that are the same length, they cancel each other out. And therefore, carbon has no vector. It has no net vector. Net vector is just whatever's left over. There's nothing left over. It's gone. There's no up and down in the first place, and these two canceled each other out. That makes carbon dioxide a nonpolar molecule. And so that's why we deal with vectors at all. Why are we doing this? Is so you can determine whether a molecule is polar or nonpolar. So what I'm having you do is just a little bit of practice working with vectors. So how do you add two vectors that are not either in the same direction or in opposite directions? Here's what you do. You create a parallelogram. A parallelogram is basically a four-sided figure where the opposite sides are parallel to each other. So what I'm going to do is I'm going to take this vector, and I need to do two things. I need to measure it. If I measure this, it's just slightly longer than an inch long. So I'm going to slide that over without twisting the ruler at all. I'm going to slide that over, and I'm going to draw a line that's exactly as long as the other. So what I've done simply is move this vector to there. Just because it's in a different location doesn't make it a different vector. It has the same exact direction if I drew it properly, and it has the same exact length. Now what I'm going to do is I'm going to do the same thing down here, except I'm going to draw a dashed line. That's the actual vector. So first of all, I want to be sure I don't twist it. I get it in the same direction, so I just slide my ruler over like that. And now it's going to be, I'm going to draw a dashed line. I'm creating a parallelogram. And then if I did that one the right length, I can just connect these two and do this with a dashed line. So now I have a parallelogram. This side is parallel to this side, and this side is parallel to this side. Now the resultant vector, these are called component vectors. The resultant vector is what I get if I simply draw a line straight across that parallelogram to the other side. So it goes like this. And so there's an arrow. So this is the resultant vector of these two vectors. Let me give you an example. Let's say this is an airplane. Let's just say that this vector is exactly twice as long as this one. It may be, it may not be. Let's say this is an airplane moving at 100 miles an hour. So this is a velocity vector rather than a force vector. So 100 miles per hour. If this vector is half as long as this original vector here, then that's 50 miles per hour. And let's say that's the wind blowing against the side of the airplane. So since I can't add these arithmetically because they're not exactly parallel or perpendicular to each other, I have to do it graphically the way I did. So here's the airplane. Here's the wind blowing this way. So what will be the result of those two coming in contact? You'll end up with the airplane being pushed off course in this direction. Instead of flying this way at 100, it's flying this way. And I'm just making up a number now, but if I actually measured this, let's say I found that to be 125 miles per hour. That means I now know by measuring, if I know the scale that this is measured to 100 miles per hour, and this was exactly half of that, if I get the ruler out and measure this, and let's say I found it to be 1.25 times as long as 100 miles an hour, that would make it 125 miles per hour, then that would be the direction and the speed of the airplane. So that's what vectors can be used for. They used to actually have a guy that did that in the cockpit of an airplane that would draw those vectors to figure out which way the plane is actually going based on wind speed and the speed of the airplane. Okay, let's do another one over here. So it doesn't matter which vector you move over to the other one. What I'm going to do in this case is I'm going to take this vector and I'm going to measure this vector, and this vector is, it's kind of an oddball length. It's not quite 1 1/4 inches, excuse me, it's not quite 3/4 of an inch, but I can see what it is. So I'm going to move it over here, slide it over here, try to keep from twisting it, and I'm going to move, and I'm going to draw the vector right there. So I just replicated this vector over here. It's the exact same vector. So now I draw the parallelogram. So I'm going to do the same thing again, except this time I'm going to draw a dash line. It's going to kind of run into my little diagram up there. That's okay. Okay, and now let's see. Let me get that right. It's going to go up to about here. Right there. And now I draw one like this. So there's the parallelogram. And now I can draw the resultant vector going like this. And that would be the resultant of adding these two vectors graphically, because they can't be added arithmetically. You can't just add the lengths of them together since they're not parallel. That would be that. Okay, what we're really going to do more in this, what we're going to do more in this unit is going in the other direction. It's taking a single resultant vector and turning it into an x component and a y component. So what does that do? It allows us to take this vector. It allows us to take this vector, and it allows us to make an x and y component, so we can add it to other vectors for which we've also taken an x and a y component. So what you're simply going to do is this. You're going to take this and you're going to draw a straight line until it gets right to the tip of this vector right here, but you want it to be along the x-axis. And if you want, you can draw the parallelogram, or the dash line. And now you're going to take this one, and you're going to make it, you want it to be even with this. So if you want, you can draw the dash line first. Be sure it's going straight across in a perfectly horizontal direction. And now you draw another vector that goes like that. Okay, so here's the x component vector and the y component vector. So we've taken this vector and we've broken it into two vectors that run along the x-y axis. Okay, go ahead and do this one over here. So we can see it's gonna go. You always start with the tail of the vector. The end that doesn't have an arrow is called the tail. The end that has the arrow is called the tip. And you're going to come down until you're even with that tip right there. And if you could do it, eyeball it like that, that's fine. You don't really have to draw the dashed lines. And now we're going to come back straight across on the x-axis, and you want it until it's even with the tip down here, and right about there does that. So there I have the component vectors. This is on the y-axis, this is on the x-axis. So what did that do for us? It allows us to add or subtract the x components of these two vectors, and to add or subtract the y components of these two vectors. Since these x components are on the same line as each other, they're both on the x-axis, that means you can add them arithmetically. If I knew that this was going 7 to the left and this one was going 5 to the right, I could say 7 minus 5 is 2. That would be 2 to the left. If I knew this one was 10 down and this one is 2 down, then I could say 10 plus 2 is 12 in the downward direction along the y-axis. So that's what this allows us to do. It allows us to then, you break a vector into its components along the x and y-axis, and then you can add the x components to each other and add the y components to each other. Okay, one more. We're not going to do that here, but it's just showing you how you can break a vector up. So we're going to just do one more here real quick, and there you go up to there. And along the x-axis, you don't even have to measure, you just have to kind of eyeball it that it goes as far as this, that you could have drawn basically a rectangle out of that. And there you go, this is the x component, and this is the y component. So that's how you break a vector into its x and y components. This one actually looks like it went a little high here, so let me dash a line there, so it really should have gone to about there. Scratch that out. Okay, it should be even with that. This one should be even with that. All right, so we'll do that when we're trying to determine the polarity of molecules. We'll use vectors.